Artificial Intelligence and Librarianship.
Martin Frick. Chapter 0. Some theoretical background to librarianship. 0.1. Concepts, classification, taxonomies, and items. A central component of classification is concepts, and a whole collection of concepts, being used at once, amount to a taxonomy or conceptual scheme or classification scheme. A concept has intension, meaning, and extension, which is the collection, or class, or set, of those items, or individuals, or things, in the world that fall under it, or are instances of it. Concepts will usually have labels, i.e. words, or names, that identify them. Some concepts can have two or more different labels. Such labels would be synonyms, e.g. attorney and lawyer. Some labels can label two different concepts. Such labels would be homographs, e.g. bank, of river, and bank, financial institution. There is a general looseness of terminology in classification areas. The terms concept, class, set, category, and probably other terms, can get used interchangeably. We will go with the flow on this, for example, often using class or set for concept. A taxonomy, unless it is a simple list or dictionary, will always have at least one class, which is a subclass of another class. Then the overall structure of the scheme might be a hierarchy, a polyhierarchy, a directed acyclic graph, a tree, a forest of trees, or some other graph-theoretic structure. 0.2. Controlled vocabularies and thesauri. In many settings, librarianship will use controlled vocabularies, CVs. A controlled vocabulary is a collection of words, or terms, where the words are controlled. They have a fixed and definite form. As to the value of CVs, Elaine Svenonius writes,
perhaps as near as one can come to generalization about the value of a CV is simply to say where precision and recall are important retrieval objectives, then a CV of some kind is mandated. Svenonius 2003, 837.
There are more detailed explanations of CVs and their value in Frick 2012, Harpring 2020, ANSI/NISO 2010, Zhang 2005. CVs are still of value in the age of computers and machine learning, as they provide a standard way to describe concepts and their relationships, and a standard interface between different systems. The simplest CVs amount to little more than lists of terms. CVs used for indexing and metadata, e.g. subject classification, tend to be more sophisticated than this. They have a structure in the background, with links or connections between some terms. As an example, the Library of Congress Subjects Headings, LCSH, is a controlled vocabulary. LCSH has hundreds of thousands of terms in it, and it took 100 years or more to build. It is probably the biggest and most elaborate CV ever made. Its size and maturity are not the only points of interest. It also relates broader and narrower terms, and it suggests preferred terms in the case of synonyms. Indexes typically use CVs. Each hierarchy in an index CV is a tree. But the index as a whole is not a single tree. There is not one single term at the top with every other term being a subterm of it. Rather, there are several different trees. The structure is that of a forest. For example, the mesh subject headings are in 16 different trees. As an illustration, here are 6 of them. 1. Anatomy. 2. Organisms. 3. Diseases. 4. Chemicals and drugs. 5. Analytical, diagnostic, and therapeutic techniques and equipment. 6. Psychiatry and psychology. Thesauri are controlled vocabularies with relations provided between broader and narrower words or terms. However, some extant controlled vocabularies themselves have broader and narrow terms, e.g. the aforementioned LCSH. If this practice is acceptable, thesauri can be much the same as controlled vocabularies. A few words are in order about the nature of the links or relations between the broader and narrower terms. International standards for thesauri distinguish three possibilities here: subclass, instance, and part, ANSI/NISO 2010. Whales are a subclass of mammals. Moby Dick is an instance of a whale. A blowhole is part of a whale. So, an imaginary CV might contain mammal narrower term whale, whale narrower term Moby Dick, and whale narrower term blowhole, whale. The first relation would be subclass, sometimes called generic, the second instance, and the third partitive. The first two relations can come under the general approach of taxonomies. The third, addressing parts, is usually considered to be mereology, which is the study of parts and wholes. We will usually assume that the collection of top-level terms in a thesaurus, those that are not narrower terms of other broader terms, could be printed, displayed, or written out in alphabetical order. There is a small wrinkle here. Just what alphabetical order amounts to is a question. To give an example, for a telephone directory, should Newark come before New York or after it? Where should numbers go? Where should foreign words go? Where should abbreviations go? The practice here is known as the filing order, and it is a matter of several decisions or conventions, which we will not go into. 0.3. Ontologies and ontological vocabularies. An ontology identifies what exists in a certain domain or area, i.e., the individuals, the properties, the classes, etc. As examples, a medical setting might have an ontology with doctors, patients, medicines, bacteria, etc. in it. A soccer game might have players, teams, balls, referees, pitches, and the like. A library might have patrons, librarians, books, desks, reading rooms, and similar items. Computer scientists use ontologies as a guide to the requisite data structures needed for their programs. Librarianship is not really interested in ontologies as such, but it is interested in the words or terms that are used. An ontology will have terms or words associated with the items that appear. So, for example, in a soccer ontology, pitch, field, and paddock are near synonyms for the surface on which the game is played. Such terms could be built into a controlled vocabulary, with pitch being the preferred term, and field and paddock being lead-in terms. A thesaurus could also easily be used here, e.g. with soccer complex having pitch as a narrower term. Ontologies themselves, or what we might call ontological vocabularies, could also be used. For example, libraries lend books, or, perhaps, libraries issue books. We can make one of these forms a preferred form and record in the ontological vocabulary that libraries lend books. Thus, ontological vocabularies, and so far as they provide relationships between words or terms, are a more general case than thesauri. For example, consider, in a medical setting, the relationships is a symptom of, may be treated by. A relevant ontological vocabulary might have preferred terms for headache, fever, influenza, and aspirin, and also such relationships as headache may be treated by aspirin. If these possibilities are thought of in a graph-theoretic sense, a thesaurus links narrower terms to broader terms, and often the structure of this will amount to a tree, i.e. there is a root, and parent nodes can have many children, but each child can have only one parent. Some thesauri, for example the LCSH, permit some terms to have more than one broader term, i.e. a child node might have more than one parent node, in which case the structure would be a directed acyclic graph, DAG. In an ontological vocabulary, any node might possibly be linked to any other node. This would amount to a general graph, i.e. a web of nodes and links. Roughly, then, an ontology is a generalization of a taxonomy, and an ontological vocabulary is a generalization of a thesaurus. 0.3. Objective, intersubjective, and subjective. These three terms are selectors among knowledge or among candidates for knowledge. When an art historian describes a painting as being in the shape or proportions of a golden rectangle, she is picking out a property of the painting. She is making a perfectly objective ascription about the external world. She can be wrong, of course. There can be some mistake with her eyes or means of measurement. Nevertheless, right or wrong, she is aiming to be objective. Moving on, suppose her aesthetic is that of neoclassicism to the exclusion of all else. She may describe a painting by Jacques-Louis David as being a good painting. That would be an intersubjective judgment. There are plenty of other neoclassicists and they would have the same view. But neoclassicism itself is not part of the external world, it is an aspect of a certain kind of culture. Finally, there is the rest of us who know nothing about art but know what we like. Expressions of what we like would be subjective. Taxonomies also can be objective, intersubjective, or subjective. Objective schemes are the province of science and mathematics. Classifying matter into atoms, elements, compounds, and mixtures, or classifying the numbers into integers, reals, or rational numbers, or classifying parts of the biological world into genus and species are all objective schemes. As noted earlier, our knowledge of the objective is fallible. Scientists or mathematicians can be mistaken, and hopefully they can correct the errors. Intersubjective schemes arise in the context of society, culture, politics, religion, myths, and the law. A good example is the Nursing Interventions Classification, NIC. It is a comprehensive, research-based, standardized classification of interventions that nurses perform. It is useful for clinical documentation, communication of care across settings, integration of data across systems and settings, effectiveness research, productivity measurement, competency evaluation, reimbursement, and curricular design. The 565 interventions in NIC, 7th edition, are grouped into 30 classes and 7 domains for ease of use. The 7 domains are physiological, basic, physiological, complex, behavioral, safety, family, health system, and community. Each intervention has a unique number, code. The classification is continually updated with an ongoing process for feedback and review. In the back of the book, there are instructions for how users can submit suggestions for modifications to existing interventions or propose a new intervention, Butcher et al. 2018. This is not a description of the external world. This is not intended to tell us how the world is built. The continual updating is a bit of giveaway on this. It is not objective in our sense of objective. Rather, it is a convenient fiction, or, as some might say, it is a social construction. However, nurses, doctors, insurance companies, etc. all respect and use this fiction. It is intersubjective. It is artifact they all agree on and use. As to the final category of pure subjective classification that, for example, is how you and I separately organize our clothes and our wardrobes. Most classification schemes in information organization are intersubjective, but some have components that supervene on objective classifications. For example, schemes for classification of resources on science or mathematics, e.g. books and research papers, would typically partially follow objective classifications that the scientists or mathematicians use. 0.4. Emotive and descriptive content. Going back to the art historian describing a painting as being in the shape or proportions of a golden rectangle. Being golden rectangular as a property is not something that is either good or bad, and it is not something that she wants to recommend to you or to warn you away from. It is just a plain description. Golden rectangular has descriptive content and little or no emotive content. When a viewer describes a painting as being nice or good, that viewer is perhaps expressing approval or recommendation. But it is unclear what in particular, if anything, in the painting, nice or good describes. Nice or good have emotive content and little or no fixed descriptive content. Emotive content is sometimes called connotation. Many adjectives, properties, nouns have both some descriptive content and some emotive content. And it is possible for different words to have the same descriptive content but different emotive content. For example, there are Bertrand Russell's well-known emotive conjugations, comment, brains trust, BBC Radio, April 26, 1948, such as I am firm, you are obstinate, he is a pig-headed fool. I am righteously indignant, you are annoyed, he is making a fuss over nothing. We made a tactical withdrawal, our allies retreated, the enemy was routed. I have reconsidered, you have changed your mind, he has gone back on his word. Were the present author to be described as firm, or as obstinate, or, indeed, as the pig-headed fool, the descriptive or cognitive content of those descriptions is exactly the same, we may suppose. That is the dispositions, and actual actions, of his that these concepts or labels pick out, if correctly used, are identical for all three labels. However, the labels are intended to either express or evoke different sentiments on the part of the speaker or the listener. Roughly, at one end, a speaker that uses firm is mildly admiring of the trait and wishes the listener to be mildly admiring also. At the other end, well, we all know what labeling the author a pig-headed fool is intended to achieve. These expressive or evocative functions are the emotive content. So, each of the concepts, firm, obstinate, pig-headed, has pretty well the same descriptive content, the same intentions, but they differ in emotive content. They are synonyms in all but emotional force. Of course, both descriptive content and emotive content of particular labels or concepts can change through time and be different across cultures. For various reasons, usually obvious ones, individuals, groups, and institutions often try to employ different labels or different classification schemes in order to manipulate the emotive-descriptive divide in a way they wish. For example, it may be that the label garbage collector is a term of mild opprobrium, and all concerned might switch to sanitary engineer as the concept or label of choice. Here, the intentions of garbage collector and sanitary engineer are pretty well the same, but one has unwanted emotional association. This move is usually a temporary palliative. Say folk do have bad feelings to, or opinions of, the profession of garbage collection. Those bad attitudes do not attach to the name, rather they attach to what those garbage collectors are and to what they do. We are all familiar with Romeo and Juliet's what's in a name. That which we call a rose by any other name would smell as sweet. Using the label sanitary engineer might work for a while, but give it 50 years and a person may be able to insult another with the words sanitary engineered. 0.5 Classification schemes and the act of classification. There are two balls that we are juggling here. There are the classification schemes, and there is the act of classification. Consider, for example, the aforementioned nursing intervention classification, Butcher et al. 2018. It is a perfectly fine classification, absolutely clear as to what it is and what it is supposed to do. Then there is the act of classification, i.e., deciding what interventions a nurse or healthcare provider have done on a particular occasion. As an example, the entry for activities relating to hypertension includes 50 to 100 activities. Here are a brief few of those. Instruct at-risk patients to have regular preventative health screenings, including electrocardiogram, echocardiogram, electrolytes, urinalysis, as indicated. Instruct related to healthy dietary pattern. Instruct related to proper physical activity, e.g., exercise 30 to 45 minutes a day. Instruct related to contributing lifestyle habits that should be avoided, e.g., use of tobacco in any form and alcohol. Instruct the patient on lifestyle modification related to sleep and rest patterns, e.g., 8 hours per night is recommended. Provide information on possible changes in lifestyle necessary to avoid future complications and control the disease process. Provide information related to the purpose and benefit of the lifestyle changes. Instruct related to self-blood pressure monitoring and to report abnormal findings. Instruct the patient on possible causes of hypertension. Instruct the patient and family to take an active role in the management of disease process, e.g., medication indications and administration, maintaining proper diet, exercise and healthy habits, quitting smoking, reducing stress, reducing weight, reducing sodium intake, reducing alcohol consumption, increasing exercise, as indicated. Instruct the patient and family on medication usage and indications. Encourage the patient and family to maintain a list of current medications and reconcile routinely at wellness checks, hospital visits, or hospital admissions. Instruct the patient to recognize and avoid situations that can cause increased BP, e.g., stress or sudden discontinuation of drug treatment. Butcher et al. 2018, pages 213 to 214. Suppose a nurse interacts with a hypertension patient and there is a serious back-and-forth medical conversation. A question is, which of these activities has the nurse done? No doubt the nurse himself and the local general medical environment know reasonably well. The point being made here is that the act of classification, deciding which items belong in which classes, is fallible, and it is subject to mistakes and possible even to deliberate misuse or malfeasance.
Chapter 1. Intellectual Background. 1.1 Introduction to Artificial Intelligence.
Artificial intelligence, AI, addresses a subset of problems that lend themselves to solution by computers, computer programs, or algorithms. Often the AI algorithms are coupled with the use of outside data. The problems in question are ones that an ideally rational and intelligent human being would be able to solve, given the time, resources, and ingenuity. One of the first examples of an AI program within librarianship is that of optical character recognition, OCR. Patrons with poor vision might not be able to read all the books that a library contains. Yet a human library assistant could read books aloud or transcribe them into Braille or some other assistive medium. In the mid-1970s, Ray Kurzweil devised and assembled computing machines that did OCR and text-to-speech synthesis. The machines could read books aloud. Kurzweil machines are a massively enabling technology, removing barriers and the access to information. At their core is an AI problem, the problem of recognizing text, i.e., classifying letters, and classifying words, where those word tokens might be of different sizes, fonts, colors, etc. AI and libraries should be distinguished both from automation and from the plain use of computers. Libraries have been taking advantage of automated processes for almost as long as there have been libraries. For example, the Gutenberg printing press, from 1440, is a form of automation. It automates the production of books and documents. Secondly, as society has benefited from the introduction of computers, so too have libraries. Computers and libraries is its own wide-ranging and active area of study, with conferences and publications. Computers and libraries includes AI uses and more besides. As examples of the more besides, the issuing and tracking of books typically will use computers and databases, as will the financial record systems for the salaries and payment of librarians. AI and libraries is different to automation and plain computing. Wherein do the differences lie? The use, or simulation, of intelligence is the main one. What about some further actual and potential examples from librarianship? There is machine translation of texts from one natural language to another. There are recommender systems that can recommend books or resources to patrons. There are, or have been, intelligent assistants in libraries, such as Stella, Beacon, or Busy, that can answer reference questions and conduct reference interviews, Sanji, Behzadi, and Gumroki 2022. There are the very familiar search engines and OPACs, online public access catalogs, / discovery systems, most of which have AI components. Final example, AI can add value to the recorded knowledge in libraries by extracting, synthesizing, and summarizing that knowledge. There is an abundance of recorded knowledge in libraries. The sheer volume of the recordings would overwhelm a librarian or team of librarians. Yet, the lithium-ion encyclopedia was written by a computer program running deep text analysis of holdings within libraries, writer 2019. AI has made massive advances in the last 30 years or so, especially in the areas of machine learning, ML, and deep learning, DL. Both these approaches involve learning. Back in 1959, Arthur Samuel wrote,
"A computer can be programmed so that it will learn to play a better game of checkers than can be played by the person who wrote the program. Furthermore, it can learn to do this when given only the rules of the game, a sense of direction, and a redundant and incomplete list of parameters which are thought to have something to do with the game, but whose correct signs and relative weights are unknown and unspecified." The principles of machine learning verified by these experiments are, of course, applicable to many other situations. Samuel 1959.
Such programs learn by playing and by associating winning and losing with various strategies, moves, and tactics. A big advance came about 50 years after this, maybe around 2010, when the amount of data that it was possible to gather, record, and process expanded massively, amounting to the so-called big data. It should be emphasized here that it is not merely the amount of data that is important, but also it is the ability to process that data with a timely throughput, Amade et al. 2019. Often this kind of learning has similarities to doing statistics with extremely large data sets. ML is distinctly different from other areas of AI, and the difference lies principally with the learning. For example, a while back, computer programs to diagnose a medical condition, say cancer, would mimic expert doctors and consultants, perhaps by attempting to extract rules governing sound or intelligent diagnoses and applying those rules. A programmer, or team of programmers, would write a program to diagnose cancer and the program would be finished and done. It is true that some tuning might be carried out after the fact, if the program was making some poor or inaccurate diagnoses. Usually, this tuning would consist of the programmer's rewriting or changing the program, not of the program modifying itself by learning. So, in general, these programs themselves did not pay a lot of attention to data that arose after they were written. This style of approach is AI by expert system. Nowadays, ML would approach diagnoses entirely differently. There would be a blank slate program that could take in vast amounts of data about different patients, and their many and varied properties, qualities, and features, data about the images and their properties, and so on. The program would be set up to focus on the label which identified whether a patient had cancer or not. Then there would be a training set, which would be data about existing patients, and even members of the public, and known data as to whether they had cancer. The program would learn which features were associated, or correlated, with the label of cancer and which not. It would be able to predict which members of the training set had cancer, hopefully with a good degree of accuracy. Then, given success, the program would be released in the world at large and applied to a test set or test cases, i.e. real cases where the diagnoses are not known. And, possibly, results for real cases will be added through time to the training set to improve performance yet further, although care would be needed were this to be attempted. You can see how in some ways this differs from diagnoses by medical doctors and consultants or by expert system. The consultants will have had years of training, of course, but they are not in any position to consider anywhere near the number of features that a program can look at. A DL program might consider thousands of features and have been trained on tens of thousands of cases. Also, while some, perhaps most, of the consultant's knowledge will be explicit, some of it will be tacit, i.e. not articulable. It would amount to perhaps vague unspeakable hunches refined by years of experience. Tacit knowledge is a problem for the prior expert system AI approach, for somehow hunches would have to be converted into rules. But if the consultants themselves cannot put this tacit knowledge into words, how is this to be done? Then, going back to consultants, tacit knowledge itself is hard to produce, instill, and disseminate. If more medical consultants are needed in the health system, the newcomers will have to go through an apprenticeship with an accomplished consultant and years of training. Of course, reproducing a computer program can be done with the click of a mouse. A question is, which system is best at cancer diagnosis? With some forms of cancer, the ML programs provide the best diagnoses. In some, with cancer diagnoses, ML can do better than both prior AI expert systems and human doctors. Deep learning, DL, is a subset of ML inspired by the human brain, in particular by neurons and neural nets. Neurons are nerve cells in the brain that can communicate with other neurons using electrical signals and synapses. Specific neurons are triggered or become excited, and that activation cascades through other neurons. This provides function to the nervous system to thinking, reasoning, responding, learning, paying attention, and other cognitive abilities. In a DL implementation, there is a network of software neurons organized in layers. Certain levels of thresholds of input features activate neurons in the first layer. In turn, first layer activated neurons activate some neurons in the second layer, and so on through several layers. At the output level, particular software units indicate, for example, whether the patient being diagnosed likely has cancer. DL is quite involved to set up, and it is demanding on resources. Large amounts of data are needed, then large amounts of training time and computing power to adjust the activation levels and various other biases. Separately, DL often can be opaque as to what is going on. By the time the triggering has gone through several layers, transparency can be lost, and that is distinctly a drawback. Here is an example, Google for Developers 2022. A cancer diagnosis DL program may learn by processing images from different hospitals. But if one of the hospitals is specifically a cancer hospital, then that feature, if used by the DL program, may result in certain types of images being given a higher probability of indicating cancer, those images sourced from the cancer hospital. And the program would be right, those images do have a higher probability of indicating cancer. But, really, this is being right for the wrong reason. You want the DL program to be analyzing the images, supplemented perhaps with facts about the patients and their histories, not reasoning from the originating hospital of the images. To guard against possibilities like these, transparency in the DL software program helps. You need to know what the program is doing, what the program is using in its reasoning. But DL programs can lack transparency. Two areas of human intelligence had proved special challenges to AI, addressing text, including languages, and translation, and addressing images. Hitherto, computers could not understand or translate natural languages, and they could not recognize and process images, including videos, as sources of information. Machine learning and DL have changed that. Text and images are now fair game for AI. AI as a scholarly discipline covers many different areas. But for the purposes of the cascade of recent AI developments and of AI in libraries, we can focus on ML and DL. 1.2. A genuine great leap forward. A great leap forward came from transformers, large language models, and foundation models. At the end of November 2022, ChatGPT was released to the public. By January 2023, it had 100 million active users. Many more interested observers were aware of its existence. More than 40% of the adults in the United States know about it. It is the fastest growing and most widely used software application of all time. There is some history to it.
In 2017, Ashish Vaswani and co-authors published the paper Attention is All You Need, Vaswani et al. 2017, see also, Huang et al. 2018. This introduced transformers. Shortly thereafter there started to emerge large language models and foundation models. What all these are will be explained later in the book. ChatGPT is a transformer and a large language model, and it is a fine-tuned version of the foundation models GPT-3 and GPT 3.5. Pretty much any machine learning or deep learning program can be built from a foundation model. That is why they are called foundation models. Also, the results of systems built using foundation models will likely be superior to any other approach. So, a correct strategy in solving a machine learning problem is to address it using a foundation model. But foundation models themselves are very expensive and resource-needy to create. We are talking here of hundreds of millions of dollars, months of computing time, and of using a large portion of the internet as data. Only a few large commercial companies have been able to produce the biggest and best of the foundation models. Producing foundation models is not the sort of thing that you and I are going to do, nor are most universities, nor even most governments. Some foundation models have been open-sourced and are freely available to all. This is a mixed blessing. Allowing programmers/users to have the code lets them see what the code is, and, historically, with open-sourced projects like Linux, the programmers can contribute, improve the code, catch bugs, etc. But foundation model ML code is a little different. There are deep security concerns and great potential for unintentional, and even intentional, harm. Trusting a few massive companies like Google, OpenAI, and Microsoft to look after us is not brilliant, but it is probably better than making the code available to all and sundry, including bad actors. That said, the massive company Meta open sources its code. Also, Hugging Face provides a hub, a library of open source foundation models, Hugging Face 2023. Some commercial foundation models have application programming interfaces, APIs, that allow users to pay a fee and use them, for now at least. For example, May 2023, from OpenAI 2022C, you can pay $20 a month and have good API access to GPT-4. From an educational point of view, we can take a machete and cleave out and discard pretty much all of machine learning prior to foundation models and start our studies at that point. Andrei Karpathy writes,
The whole setting of training a neural network from scratch on some target task, like digit recognition, is quickly becoming outdated due to fine-tuning, especially with the emergence of foundation models like GPT. These foundation models are trained by only a few institutions with substantial computing resources, and most applications are achieved via lightweight fine-tuning of part of the network, prompt engineering, or an optional step of data or model distillation into smaller, special-purpose inference networks. I think we should expect this trend to be very much alive, and indeed, intensify. In its most extreme extrapolation, you will not want to train any neural networks at all. Karpathy 2023b.
1.3 Digitization and Transcription. Digital computers work with electronic digits, surprise. They work with the digits 0s and 1, or, to phrase it differently, with the booleans false and true. But, unfortunately, at least some of the information resources that the ML algorithms have the potential to address are not, or were not, in digital form. For example, Shakespeare's only surviving playscript The Book of Sir Thomas More was not, British Library 2020. So, digitization of those resources not born digital is an important precursor to wide-ranging ML and librarianship. The 2002 Google Books Project, or Google Project Ocean, was a very early attempt to address digitization. Its approach was to use OCR scanning on the physical resources. It was not prompted by the needs of ML, rather it was aiming for a universal library. As James Summers writes, You are going to get one-click access to the full text of nearly every book that's ever been published. Books still in print you'd have to pay for, but everything else a collection slated to grow larger than the holdings at the Library of Congress, Harvard, the University of Michigan, at any of the great national libraries of Europe would have been available for free at terminals that were going to be placed in every local library that wanted one. At the terminal you were going to be able to search tens of millions of books and read every page of any book you found. You'd be able to highlight passages and make annotations and share them. For the first time, you'd be able to pinpoint an idea somewhere inside the vastness of the printed record and send somebody straight to it with a link. Books would become as instantly available, searchable, copy-pastable as alive in the digital world as web pages. Summers 2017. There's another huge potential benefit that arises from the network effects of having many books digitized collectively. The Google PageRank algorithm, which the core of its very successful search engine for the web, uses links between web pages to establish ranking. Something similar, citation indexing, citation counting, and citation ranking, had long been in use in bibliometrics and informatics working with paper-based libraries, Dizeix 2011, Araujo, Castagna, and Jorlin 2021. If books, journals, and other paper-based resources were also to be available digitally, powerful algorithms using linking then could be used in conjunction with massive compute power. Search and ranking of actual books in libraries would be able to be improved. So, the promise was of a universal library with improved search and ranking of the sources. Unfortunately, the Google Book Project got mired in difficulties of one kind or another, mainly legal, and, as of 2023, it seems to have drifted off into limbo. Summers 2017, Howard 2017. The work does continue, but in a somewhat slower and piecemeal fashion. We cannot pretend that this is a good result, but modern practices have rendered it less of a total disaster than it might have been. Most published books today are written on word processors on computers. Even if they are not produced that way, they are usually in electronic form prior to being printed, if, indeed, they are printed. The authors or publishers may or may not make the electronic form available to the world at large. Authors write books to have them read. Publishers print books to have them read and sold or licensed. The parties concerned have incentives. So, one way or another, these electronic forms should become available. Separately, physical documents themselves are perhaps not so important as they once were. The indexed web is around 60 billion pages, Decunder 2022, and Google estimated that the number of physical books they needed to scan was around 130 million. The web, the internet, is a lot larger than the combined book collections and libraries. There is a distinction or consideration that should be mentioned here, that between digitization and transcription or decoding. Were we to use a modern smartphone to take images of Shakespeare's The Book of Sir Thomas More, we would have the playscript in digital form as zeros and ones. But the playscript itself is in letters, words, sentences, and in speeches. It has structure. It is that structure, or some or most of it, that we would like captured digital form. When Google set out on their book project, they did not aim to photograph every page of every book. They aimed to use optical character recognition, OCR, to get to the structured text in digital form. They aimed to transcribe to digitized computer text that could be copied, pasted, read aloud, translated to other languages, etc. It is that structured digitization that is the desired goal. ML can usually work with a digital image of a text and do an OCR extraction of structured text. But, nowadays, when authors are writing on word processors and publishers are using the digitized form throughout the workflow, structured digitization should be available without having use OCR on images. Many libraries have digital collections. For example, the Library of Congress has https://www.loc.gov/collections with millions and millions of items. Its collection chronicling America, Historic American Newspapers, has over 20 million images, i.e. photographs, of pages of historical newspapers. That is great, but for certain kinds of research those need to be transcribed into the zeros and ones of computer text. Very shortly, machine learning will be able to do that task in the blink of an eye. 1.4. Appear to text in structured digital form. Having text in digital form is very valuable in terms of what can be done with it. Here are some possibilities. There may be some overlap between the categories. 1.4. 1. Text-to-speech. Computer text can be spoken aloud. That is one part of what the Kurzweil machines, mentioned above, do. This is not trivial, by any manner of means, but it is also not a challenging AI problem. Obviously, text-to-speech computer programs need to know the language of the text and how it is to be spoken, its pronunciation. 1.4.2 Machine translation. Computer text, from a source natural language, can be translated by computer into other languages. This used to be done in an expert system style of AI. There would be a dictionary between the source and target languages, grammar rules for both languages, and programmers would try to figure out translation rules that algorithms could use to get from one language to the other. The modern approach would be to use ML and DL. This relies on existing, human, translations between texts. These come from a variety of sources. For example, the United Nations provides translations into 6 languages of all its texts. The Bible has been translated into many languages, although it does have the drawback of having a very specific and distinctive written style. Google Translate uses the DL program Google Neural Machine Translation. At a first cut, this is what it does. There are a number of texts that have been translated by human translators from one language to another, say from English to French and French to English. To translate from English to French, the Neural DL will find all the existing occurrences of the relevant sentence, phrase, or word in English and look up how they've been translated by the human translators. Then it will favor what seems to be the best translation. Making the latter judgment depends also on what the DL has learned, supplementary rules, dictionaries, etc. The resulting translations are reasonable, but not perfect. They can be improved by further editing by human readers or translators. You can see where some of the problems may lie. Context is one. Single words might be homographs, for example, bank, financial institution, and bank, side of a river, and the translation system might lack the context to disambiguate them. Plain lack of understanding may be another. Human translators presumably will understand their translation, and this would prevent certain kinds of ridiculousness. In a general way, a neural DL will learn what is silly and what is not. But still, in no sense does it understand the text, and this leaves open to making certain kinds of mistakes, i.e. those where the words, grammar, and construction are all fine but the result is nonsense. Douglas Hofstadter offers interesting examples, including:
In their house, everything comes in pairs. There's his car and her car, his towels and her towels, and his library and hers. Hofstadter 2018.
As of 2023, machine translation simply cannot translate this correctly, say from English to French. An anecdote. The author's wife had some dental treatment while living in Japan. The Japanese hygienist had a little device that she spoke into in Japanese, and it spoke back in English. So, this is digitization and transcription of speech, translation of one language to another, then speaking aloud the resulting translation. Here's a real example of what it said to her: "Pardon me, may I please put red dye on your dirty teeth?" Despite the occasional oddity, machine translation can work 24 hours a day, 7 days a week on a vast number of sources. It is not expensive. In sum, machine translation can produce a bulk of translations of reasonable quality. Progress in this area is rapid. For example, Ankur Bafna and co-authors have a paper building machine translation systems for the next 1,000 languages, Bafna et al. 2022. 1.4. Search and navigation. Once a text is in digital form, it can be searched and navigated very efficiently, even if it has no preemptively prepared index. For example, the words butterflies and Rapalosera are synonyms, and Lepidoptera is a term for an order of insects that includes Rhopalocera, i.e., it is a more general term. Imagine yourself to be a young person with a physical book on the subject of insects. You are interested in the specific topic of butterflies. But perhaps the word butterflies is not in the index of the book, nor does it appear frequently in the text, if at all, although Rhopalocera appears many times, being the favored word of the synonym pair. Also, on this occasion, you are interested more widely in insects. You would like your search to include butterflies, but also, in part, to be a little more general. Basically, you will be disappointed with what you are able to achieve, which will be more or less nothing. In contrast, with a book to be digitized and it were searched by computer, either with large language model or with thesaurus support, the desired tasks and goal would be trivial and satisfiable in milliseconds. 1.4. For preservation and archiving. Loss of the contents of some texts could be catastrophic, for example, contracts, treaties, or the works of Shakespeare. Once digitized, once there is a digital surrogate, there are cryptographic techniques to preserve text surrogates forever. They could be encrypted, hashed, and put into a suitable public blockchain using content-based indexing. Alternatively, one digital copy could be placed in the billion-year archive through the good graces of the Arch Mission Foundation, Spivak and Slavin 2023. 1.4. 5 free books. Once text is in digital form, the marginal cost of duplication is near zero. Of course, there are considerations of licensing and intellectual property. 1.4. 6 Natural language processing. Natural language processing, NLP, has always used zeros and ones and computers. But it has absolutely flourished with ML, and especially with large language models, which we will discuss later. As a selection of possible procedures or techniques, there is the entire field of digital humanities, text summarization, text mining, question answering, information extraction, text categorization, sentiment analysis, plagiarism detection, author and genre recognition, word sense disambiguation, and lexical and ontological acquisition, and text analysis for social applications such as blogs and social networks. So, for example, given 2 physical texts by unknown authors and the question, are these texts written by the same author, digitization and NLP can provide the answer. 1.4. 7 Processing by computer software. Much data either exists or was initially recorded on a physical medium, such as paper or cards. This data really needs to be digitized in order to be processed by statistics or data science. This processing would then amount to data processing, or data mining, or text data mining, TDM. Vast continents of knowledge or information would be opened up. 1.5. Data and the need for good data. ML aims to learn, and what it is going to learn from is data. Primarily, this data is the encoding of observational or experiential reports about the world. At one point, historically, such data would have been assumed to be a solid bedrock. Nowadays, most philosophers of science would describe observation reports, or data of this kind, as being theory-laden. Really, there are 2 aspects to this assertion. Any observation report relies on theories which infuse either the instruments used or the raw observations, if there is any such thing as truly raw observations. Duhem 1914, Hansen 1958. Duhem writes,
Go into this laboratory, draw near this table crowded with so much apparatus, an electric battery, copper wires wrapped in silk, vessels filled with mercury, coils, a small iron bar carrying a mirror. An observer plunges the metallic stem of a rod, mounted with rubber, into small holes. The iron oscillates and, by means of the mirror tied to it, sends a beam of light over to a celluloid ruler, and the observer follows the movement of the light beam on it. There, no doubt, you have an experiment. By means of the vibration of this spot of light, the physicist minutely observes the oscillations of the piece of iron. Ask him now what he is doing. Is he going to answer, I am studying the oscillations of the piece of iron carrying this mirror? No, he will tell you that he is measuring the electrical resistance of a coil. If you are astonished and ask him what meaning these words have, and what relation they have to the phenomena he has perceived and which you have at the same time perceived, he will reply that your question would require some very long explanations, and he will recommend that you take a course in electricity. It is indeed the case that the experiment that you have seen done, like any experiment in physics, involves two parts. In the first place, it consists in the observation of certain facts. In the second place, it consists in the interpretation of those facts. The result of the operations in which an experimental physicist is engaged is by no means the perception of a group of concrete facts, it is the formation of a judgment interrelating certain abstract and symbolic ideas which theories alone correlate with the facts really observed. Duhem 1914.
A consequence of this is that the reports are conjectural or fallible. Any of them may be mistaken. They are not a bedrock. Second, any collection of data is a selection among what it is possible to observe or measure. The philosopher of science Karl Popper writes,
"The belief that we can start with pure observation alone, without anything in the nature of a theory, is absurd, as may be illustrated by the story of the man who dedicated his life to natural science, wrote down everything he could observe, and bequeathed his priceless collection of observations to the Royal Society to be used as evidence." This story should show us that though beetles may profitably be collected, observations may not. 25 years ago, I tried to bring home the same point to a group of physics students in Vienna by beginning a lecture with the following instructions: take pencil and paper, carefully observe, and write down what you have observed. They asked, of course, what I wanted them to observe. Clearly the instruction, observe, is absurd. It is not even idiomatic, unless the object of the transitive verb can be taken as understood. Observation is always selective. It needs a chosen object, a definite task, an interest, a point of view, a problem. And its description presupposes a descriptive language, with property words. It presupposes similarity and classification, which in their turn presuppose interests, points of view, and problems. Popper 1963.
So, the data used in ML is always incomplete. It is becoming increasingly common in ML circles to use the phrases ground truth or ground truths or ground truth data set. Caution is needed here. No matter how much care goes into gathering and curating the data, it can still be wrong and incomplete. There are many other pitfalls that can occur: sample data or training data, even if the data is absolutely correct. The data may be unbalanced. An example that can be used here is that of a test predicting the unknown gender of a person from their known height. If the training data, the sample, where the heights and genders are known, consists of 95% males and 5% females, then mathematics will suggest predicting male no matter what the height of the test subject is. In sum, getting good training data is tricky. 1.6 Types of Machine Learning. 1.6 1. Supervised. Supervised learning is learning with a teacher who knows the answers. An example will help here: optical character recognition, OCR. OCR is a solution, a supervised classification problem. It can look at some text, e.g., call me Ishmael, and identify, or recognize, that the first letter of the text is a C, the second letter is an A, and so on. MLOCR will approach this by being taught how to classify characters. It will be supplied with a training set, which will be a reasonable sample of letters and the correct classifications of what they are. Training sets are typically fairly large. For example, the well-known and widely used NIST set, which is a collection of handwritten examples of the digits 0 through 9, with correct identification labels, has around 60,000 entries. LeCun, Cortez, and Burgess 1998. The overall OCR technique is an optical one, so it is the features of the sample letters that can be detected optically that will be the input, e.g. size, shape, color, grid arrangement of component dots or pixels, etc. Then the program will attempt to correlate combinations, i.e. vectors, of these with the correct classification, e.g. that a particular sample token character is an A. More than likely, the program will make many mistakes initially. But either the programmers, or the program itself, will tune various parameters, e.g. weights on the components of the vectors, to improve the classification until it reaches an acceptable level of performance. There is an interesting point to be made here about what area known in statistics as omitted variables. As mentioned, the ML program will start by considering optical input from size, color, pixels, etc. But it will then learn which variables of these to include and which to omit. The machine here has an advantage over a human statistician as it has the sheer computing power to run through the alternative possibilities in a reasonable time. The training set needs to be adequate for the task. For example, if the letter J does not appear in the training set, it is unreasonable to expect the ML program to classify JS correctly. Even if JS appear, there needs to be enough of them in the various fonts and scripts, cursive or not, monospaced or proportional, etc., for the program to be able to learn what is correct and what is not. OCR, i.e. recognizing the actual individual characters, would not usually be an end in itself. Rather, the interest would be in the words that those characters form, or, more generally, the text. If the OCR, or text recognition, application has access to a wider context of text, that can improve its performance. For example, if the ML is recognizing entire words from their component characters and separators, then the first letter of the word on is going to be the letter uppercase O and not the numeric letter 00. The number 0 makes no sense in that context. Supervised learning needs labeled data for its training data. Getting such data with quality and in quantity is not easy. Often experts will be required to do the labeling, e.g. of medical images, or of the correct cataloging numbers for books in libraries. But many experts would struggle if confronted with 100,000 items to label. Sometimes the process can be eased, at a financial cost, by crowdsourcing, Wikipedia 2023b. For example, the Lambda models of dialogue agents uses crowdsourcing, where the members of the crowd are supplied with calculators and access to a web browser and a search engine so they can check how reliable the output information is that the dialogue agents supply. Thopolin et al. 2022. 1.6.2 Unsupervised. The word supervised comes into qualify learning because it is known, for most of the cases, what the correct answers are. A machine learner could, alternatively, be challenged to classify marks, characters, on paper into groups of marks, characters, similar to other characters, i.e. clustering, forming clusters of similar characters. That would be unsupervised learning, where there are no known right or wrong answers, and no teacher. A first issue here is that there is no ML constraint as to how many clusters there might be, or should be, in any given problem. For example, the music streamer Spotify plays songs that the listener wishes to listen to. Spotify can cluster these songs into similar songs and perhaps mark those as being playlists or radio stations. Then the user can listen to a radio station while cooking, or while going for a walk, etc. But the clustering algorithm needs to know how many radio stations should there be: 2 stations, 7 stations, 300. There is no answer to that question from within the ML system. Spotify itself, or the user, or some outside party, has to decide on the number of stations. Going back to OCR, and attempting to do it in an unsupervised fashion. We could help it by saying we would like 36 clusters. We have in mind here one for each letter of the alphabet, and for each digit. Clustering might then lead to mistakes like characters that we consider to be uppercase I's being put together with lowercase l's or 00 with uppercase O's. There is no training set. There are no right or wrong answers available to assess the program. Unsupervised classification might be perfect in certain areas. For example, clustering songs into playlists, but it is not really suitable for OCR. 1.6.3 Semi-supervised. Supervised and unsupervised classification approaches can be combined. This might be useful when there is a huge amount of data, of which only a small proportion is labeled, i.e., it is known what those items are, and the process of labeling is expensive or time-consuming or hard to do. For example, imagine some historical biodiversity researchers who collected specimen samples in the style of Darwin. They also did as much labeling as they could manage, including labeling at least one example of what they thought was every species they came across. Then the initially unlabeled specimens were later to be donated to many museums, who, of course, wanted them labeled. This problem might be approached by clustering, supplemented with a back and forth with supervised learning. Then, the final labeling of the museum samples could be done by machine. 1.6.4 Self-supervised. The learning techniques mentioned to date have problems and issues. Supervised learning required large amounts of labeled data, which is often difficult, expensive, or even near impossible to obtain. The need for the quality labeling is the cause of the problem. Unsupervised learning simply might not give you what you want. Self-supervised learning, SSL, is an ingenious idea which will often be far superior to its alternatives. Basically, it uses unsupervised learning, and the data itself, to label the data, then it uses supervised learning on the now labeled data. To do this, the data has to have suitable structure or patterns in it. This gives a context, or contexts to items of data, and the general problem being addressed needs to be tightly specified or understood. SSL really found its place in natural language processing, NLP, and some examples from NLP may make the technique clearer. The foundation models BERT and GPT-3 both have the pre-training task of predicting the next word or previous word from a sequence of words in a passage of English or other natural languages. Devlin et al. 2019. Brown et al. 2020. The way they do it is to scan vast amounts of English text, e.g. trillions of word tokens such as the entire of the Internet, including Wikipedia, Reddit-linked sources, all freely available digitized novels, etc. Apparently GPT-3 was pre-trained on 45 terabytes of data. This is about the same size as 1/4 of the holdings of the Library of Congress. This pre-training provides the various transition probabilities from prefix or suffix, words or sequences, to the current target word, and, essentially, the solution. Now, the data itself, the English text, is not labeled, so this is not supervised learning. But the scanning of the text can produce a pseudo-label for the missing gap word. For example, the label for "the cat sat on the" label can be produced merely by looking through a vast amount of real-life text. Of course, there does not have to be a single one-word answer to this. Mat, table, floor, etc. might all be possible answers. But then there will be probabilities associated with the possible answers, and the wider context will provide guidance. Self-supervised learning has an obvious home with natural language. But it also can be used with images. There is a context to which patches of colors or pixels are close to other patches. Further, foundation models like GPT-3 are multimodal. They can be pre-trained, using SSL on text, then fine-tuned, perhaps with some prompts or labeling, to work on images. SSL offers freedom. Getting good, labeled data at scale is difficult, if not near impossible. It is a barrier or bottleneck. But with SSL, it is not needed. 1.5.5 Reinforcement. Reinforcement learning is familiar to us in daily life. It involves exploration of an environment by trial and error, and, as part of this, having what are called delayed rewards. Sutton and Bartow, 2018. The rewards provide feedback as to how well the trial and error is working. Imagine a student backpacker having temporary employment picking apples in an orchard. She gets paid for each apple she picks, but for each apple she picks there will be one less apple to pick on the tree that she picked it from. Also, she gets a bonus for each basket of apples that she picks, especially if she fills the basket faster than other pickers. Bigger apples will fill a basket quicker, but there will be a lesser number of them in the basket. We will assume here that she is trying to maximize her pay, i.e. her rewards. Quite what her best picking strategy might be is a bit of a question. She presumably will have to change trees from time to time, but changing trees is not actually picking. It amounts to dead time invested in the hope of higher rewards later. She will also have to pay attention to other pickers and to the simple nature of the individual trees. If she works in the orchard for several days, she should be able to learn of a reasonable strategy by trial and error, i.e. by trying a few approaches and favoring those yielding higher total rewards. The whole process amounts to reinforcement learning. Reinforcement learning can be used when the ML system has to make a sequence of tasks, or moves, or steps towards some desired goal and there are rewards or penalties for successes or failures. While learning, the system will typically be allowed to try the overall task of reaching the goal many times. Games are a good setting for this, e.g. tic-tac-toe or checkers or chess. There will be an environment and possibly permitted moves governed by rules. The system will be rewarded or penalized according to whether a particular move is judged to be good and also, perhaps, whether the system wins or loses the game overall. The system is not programmed with any strategy or tactics, rather it explores the game by trial and error. Another example of reinforcement learning would be a robot exploring an environment, e.g. finding a route through a maze. Reinforcement learning is not supervised learning, there is no labeled data. It also is not unsupervised learning or self-supervised learning. It is a sui generis ML technique, one that needs to have some reward structure. It certainly can be used in language settings. For example, an ML program might be configured to produce 5 different translations of the same text. Then if these could be ranked, perhaps by a human judge, then the rankings could be used as a reward structure, and a reinforcement learning system introduced improve the system at translating. Sometimes, in this context, the reward structure is called the reward model. Typically, reinforcement learning is very compute-intensive, e.g. for chess, the ML system may need to play hundreds of thousands of games. There are many algorithms to produce reinforcement learning, but few, if any, are efficient in really large settings. Supposedly, one of the technologies that enabled some of the uses of large language models, such as ChatGPT, was the invention of proximal policy optimization, OpenAI 2017. Proximal policy optimization is a reinforcement learning algorithm.
1.7 The concept of algorithm. Programmers, mathematicians, and computer scientists regard algorithms as finite sequences of steps or instructions to perform a computation. The instructions themselves are considered to be atomic or not in need of further breakdown or explanation. The earliest algorithms are from about 3,500 years ago. Here's one from that period to do division of integers by repeated subtraction. It is assumed that we can determine whether one number is smaller than another, that we can subtract one number from another, and that we can count the number of subtractions that we have done. Then the divisor is repeatedly subtracted until the remainder is less than the divisor. Finally, the quotient, the result, is the number of subtractions that have been made. For example, to determine the quotient when 22 is divided by 4, which we all know to be 522 minus 4 is equal to 1822 minus 4 minus 4 is equal to 1422 minus 4 minus 4 minus 4 is equal to 1022 minus 4 minus 4 minus 4 minus 4 is equal to 6. 22 minus 4 minus 4 minus 4 minus 4 minus 4 is equal to 2 * and 2 is less than 4 * 5 subtractions have been made, so the quotient when 22 is divided by 4 is 5.
This algorithm is taught in third-grade school mathematics. The act of programming is using a computer programming language to assemble instructions into algorithms. Usually, this process will be modularized. Small algorithms will be created as components or modules. Then these algorithmic modules will be combined to produce a complex artifact. The end result might be described as being an algorithm, but, given sufficient complexity, the plain moniker computer program might be more suitable. Google's Internet services consist of 2 billion lines of code. Microsoft's Office suite for the Mac consists of 30 million lines of code. Desjardins 2017. It would be very strange for programmers or computer scientists to describe either of these as being algorithms. They are computer programs or collections of computer programs. The word algorithm has become transmogrified in recent times. The vernacular has taken a different turn. Where there is no apparent human agency in a computer program or computer-supported service that affects humans, folk can and do ascribe the agency to an algorithm or algorithms. For example, nowadays a mortgage company will typically use data, computers, and algorithms to determine whether we might qualify for a loan. If we are turned down, we might well say that the mortgage company's algorithm, the algorithm itself, declared us ineligible for one of their loans. This attribution is not quite right. We will go into that further in section 5.1. There is an important detail in connection with algorithms in the context of ML. It is that algorithms can change or self-adjust or self-adapt when faced with training data. The ML programs learn by changing their algorithms. The same beginning, template, or seed algorithm when confronted with two different sets of training data can produce two different trained outcome algorithms. Perhaps that is not a surprise. One would expect different learning from different data to learn from. This adaptation is a small change from how historical algorithms typically behaved, and it can mean, in particular cases, that it is unclear or unknown as to which algorithm is actually running after learning. In turn, this can shroud some or many of the processes in a fog, i.e. in black boxes. This is exactly the opposite of what desirable. Transparency is valuable both for ethical reasons, for example, when making decisions involving humans, and for technical reasons, for example, when trying to assess the correctness of the programs. Part of the lack of transparency comes from the plain complexity of the systems. Some of the ML systems might have 1 billion parameters or more, then it becomes hard to know what the values for the parameters are and how they interact. There is another word or label that gets used in this context, and that is model. When an ML system is trained and its initial algorithm adapts and changes into another algorithm, known or unknown, transparent or hidden, the end result is often called the model.
Chapter 2. Chatbots. 2.1 Introduction.
The word chatbots is commonly used in AI as a label for dialogue agents. In turn, dialogue agents might be chit-chat agents or task-oriented agents, Daniel Jurafsky and Martin 2021. Chit-chat agents are understood to be software systems that can chat with you. They chat by interchanging text messages or by using sound and speaking and listening. There is no special purpose to these chats, apart from entertainment, engagement, and perhaps companionship. Task-oriented dialogue agents also have interactive sequential conversations. But they can do more and do less. For example, in a general setting, they can book an airline ticket, order a taxi or meal, set an alarm or timer, produce a recipe for a birthday cake, retrieve information resources, offer instruction, etc. Most everybody is familiar with Apple's Siri, or Windows Cortana, or Amazon's Alexa, or OK Google, which are such agents. These are used on many devices including, most obviously, smartphones. The task-oriented agents can do less in the following sense. They are directed to one task, or sometimes more, and this really limits the possibilities they have to face. For example, an airline ticket agent needs to be able to chat about departures, destinations, and flight times, but it does not need to be able to chit-chat about the novels of Toni Morrison, last night's baseball game, and how to cure a shank at golf. There is a suggestion that chatbots may partially replace browsing of certain kinds of web pages. For example, a library home page may have a lot of information on it about the various services or resources that the library offers. Navigation through this may be eased by assistance from a chatbot. 2.2 Dialogue Processing.
Among the hallmarks of natural dialogues are unexpected and seemingly unpredictable sequences of events. Bobrow et al. 1977.
It is valuable to have some appreciation of what a dialogue is and how difficult it is to model it using software and natural language processing, NLP. We will make simplifications here. A dialogue is a communication that takes place between two or more participants. For us, this can be two participants, one of which is a human and the other a computer or software system. At the beginning of the dialogue, one of the participants has the initiative or control. This means that they set the initial agenda, assumptions, and common understandings that are required for the dialogue to get underway. There are different conversational settings. As examples, talking about Christmas gifts for children has different assumptions to that of discussing the best recipe for a bundt cake or to that of booking an airline ticket. Of course, a single conversation can range over many settings. As the dialogue progresses, it may be that the agent with the initiative retains it throughout. An example here would that of a commercial telephone answering and routing system. The caller can make choices among the options on offer, but the caller cannot ask questions or offer choices to the system. More usual are dialogues of mixed initiative, where control is sometimes with one agent and sometimes with the other. This usually would be the case with airline ticket reservation systems. The participants can take turns at having the initiative, but also one can retain the initiative through several interactions, for example, with a sequence of yes/no questions. How the initiative might be transferred from one to the other is a complex array of possibilities. There are a number of explicit conversational practices, but also there are implicit conventions, e.g. pauses. Also, an important consideration is whether there are visual or nonverbal cues, as there might be with video conferencing. There are indexicals, such as I, now, yesterday, etc. Just what these might refer on a particular occasion to is a bit of a question. The computer saying I will have a different reference to the human saying I. But also the indexicals might change their reference as the conversation progresses and the initiative changes. 3 days earlier might refer to different times at different points in the conversation. Sometimes the notion of anaphora is introduced here. Anaphora is where the interpretation or reference of one expression depends on another. For example, in John Smith is conscientious. He often works evenings. The word he is anaphoric for John Smith. The computer can avoid anaphora, perhaps at the cost of having a somewhat stilted and unusual conversational style, by always making the references explicit, e.g. saying John Smith instead of he. However, there is no controlling what the human might do. Further, there is conversational implicature, studied extensively by the philosopher H.P. Grice, Davis 2019. This is where speaker meaning is different to sentence meaning and similar related phenomena. Consider an example from Davis 2019. Alan, are you going to Paul's party? Barb, I have to work. The meaning of the sentence that Barb says is that she has to work. The sentence itself does not have any kind of meaning like not going to a party. However, her use of this sentence on this occasion means she is not going to Paul's party. There is a conversational implicature to that effect. So, for example, if a chatbot is collecting RSVPs to Paul's party, it needs to understand I have to work as meaning I am not coming. There are sentence fragments. For example, answers to questions might be single words or phrases, and grammatically they might be almost anything: nouns, adjectives, verbs, noun phrases, etc. From a logical point of view, we would expect a linguistic component to be either a reference to an item or be a true or false statement about items referred to. But extracting what is what from a fragment might require looking back through to dialogue, to earlier questions or context. Bobrow et al. 1977 have the example computer, and what name should I make the reservation, please? Client: Dan Bobrow. Now the Dan Bobrow is a reference to a person, and not a sentence or statement, but what is happening here is that the assertion you should make the reservation in the name of Dan Bobrow is being made, but to determine that the question and earlier context are needed. And some dialogues are not easy to process. 2.3 ELIZA to Alice. ELIZA was introduced by Joseph Weizenbaum in the paper ELIZA, a computer program for the study of natural language communication between man and machine, Weizenbaum 1966. ELIZA is the first chatbot. It is an early, indeed very early, AI program. However, it is not a ML program. As we will see shortly, it works by rules and pattern substitution. We have an historical interest in ELIZA. Also, its way of manipulating strings, playing with form not meaning, is something of style common in modern machine-learned natural language processing. Here is a transcript of a typical conversation with ELIZA. Men are all alike. In what way? They're always bugging us about something or other. Can you think of a specific example? Well, my boyfriend made me come here. Your boyfriend made you come here. He says I'm depressed much of the time. I am sorry to hear you are depressed. It's true, I am unhappy. Do you think coming here will help you not to be unhappy, and so on? The human correspondence utterances are shown in lowercase, ELIZA's replies in uppercase. This extract is from Weizenbaum 1966. As Weizenbaum tells us, the conversation style here intended to be between a patient and a Rogerian psychotherapist. There is an important sleight of hand in this. A Rogerian psychotherapist feeds, or replies, back some variation of what the patient has said. The psychotherapist does not say anything that requires knowledge of the world. This matters because ELIZA does not then need any knowledge. So, this might be a conversational fragment. I went for a long boat ride. Tell me about boats. But a request for knowledge would meet with avoidance, perhaps. What is a boat? Have you always been interested in boats? The basic computational procedure for ELIZA is simple. The input text is inspected for one or more matches to patterns. A pattern here usually amounts to a string, where some parts are literals and other parts are variables. So, for example, if we use x, y, etc. as variables, then I feel x is a pattern, the I feel part is a literal, and the x is a variable. The matching process takes some input text and a pattern, or patterns, and sees whether they can be matched. For example, I feel X can be matched with I feel sad, or, indeed, I feel sick, I feel happy, I feel cold, etc., but not matched with I read novels. Then there are rules which dictate how the matched results are to be transformed. For example, rule number 3, I feel X, is to be transformed to do you often feel X, where, of course, the value for X is substituted back in. Usually, several different patterns will match the input text. Then each of those patterns might have several different transformation rules that apply. What happens here is that there is a randomizer which makes a choice of what to use. The reason for this randomization is that it allows ELIZA to produce different responses to the same input text. So, each conversation or session will usually be slightly different to earlier ones. At this point, ELIZA can be improved by adding some memory of the conversation or correspondent, being more sophisticated with the responses, and so forth. There are ELIZA-like chatbots alive and well today, most notably ALICE, Artificial Linguistic Internet Computer Entity, Wikipedia 2022c. There are two important points to note about ELIZA systems. What they do is trivial substitution of one piece of text for another. Merely by looking at the source code and a transcript for a session, you can see which patterns and rules were used, step by step. The inner workings are crystal clear. There is no mystery here, nor any intelligence. Nevertheless, a good proportion of folk think that ELIZA systems are intelligent, or even that, when talking with ELIZA, that they are conversing with a human. Weizenbaum noted this in his original paper, and in 1972 the ELIZA system passed the Turing test, i.e. fooled some people into thinking it was human. Weizenbaum 1966, Colby et al. 1972. 2.4 The Turing test. Are you wondering what the Turing test is? Here is ChatGPT's explanation of it, provided on December 6, 2022, while ChatGPT was available as a research preview. 2.5 Machine Learning Chit-Chat Bots. ML systems can learn to chit-chat. They do need data of conversations, and a large quantity of it. There are databases, or datasets, of conversations, e.g. of telephone conversations. Then dialogues from movies are a good source. Also, sometimes, crowdsourcing is used. People either volunteer or are paid to converse in an interesting and potentially useful way. Roughly speaking, the systems can either retrieve or generate. Retrieval systems will look through the conversations that they are aware of and select fragments similar to the one they are addressing, make a choice or ranking among the fragments, then return a suitable response. Generative systems can generate a response. They learn from their training and subsequent conversations what might be suitable in which circumstances. In a sense, they are learning rules. But there are not a fixed number of rules programmed in before the system starts learning. The responses that generative systems produce can be novel or new. 2.6 Lambda. Lambda, from Google, is a family of language models for dialogue applications, Thoppelin et al. 2022. These models are for chit-chat bots. We will briefly describe here what they were designed for and what they can do, and in Chapter 3 we will go into a little more technical detail. Lambda agents should be able to supply conversational quality in dialogues lasting 20 turns or more. What they say should be safe. It should be safe, period. Some earlier non-Lambda dialogue agents have suggested that their conversational partners eat ground glass as a treatment for a medical condition. This is not a good or desirable outcome. Additionally, the dialogue agent should not offer any views that are biased or toxic. Finally, the conversational contribution needs to be grounded. One might take grounded to mean that the views expressed be true and supported by evidence. But that condition is too strong in as much as there are many areas where there are competing rival views and where all the views have some reasonableness to them. Grounded is just the requirement that if the agent professes opinions offered as factual, then those opinions need not to be fictional or hallucinatory. Historically, conversational agents have been known occasionally to offer plausible assertions which are pure fantasy. 2.7 ChatGPT. ChatGPT was produced by OpenAI. ChatGPT itself tells us about OpenAI. OpenAI is a research institute that was founded in 2015 by a group of entrepreneurs, researchers, and investors who were interested in advancing the field of artificial intelligence. The organization was created with the goal of promoting and developing friendly AI, which is AI that is aligned with human values and capable of working towards the benefit of humanity. Since its founding, OpenAI has become one of the leading organizations in the field of AI research and has made significant contributions to the development of ML algorithms and technologies. Some of the notable achievements of OpenAI include the development of the GPT-3 language model, which is one of the most advanced natural language processing systems in the world, and the creation of the DALL-E artificial intelligence system, which is capable of generating images from text descriptions. Overall, OpenAI has played a major role in advancing the field of AI and in fostering the development of safe and beneficial AI technologies. ChatGPT output to the question, "What is the history of OpenAI?" December 15, 2022. ChatGPT is a large language model, LLM, or a foundation model. Quite what those features are will be explained in the next chapters. The LLM chatbots are so much in advance of all the other earlier chatbots that the earlier ones are mostly rendered obsolete and of historical interest only. As of November 2022, ChatGPT was a chat front-end to GPT 3.5, OpenAI 2022a. GPT 3.5 itself is a generative, pre-trained, transformer, iteration 3.5. Generative here means that it can predict or generate new output. Pre-trained means that it has a two-stage training. First a pre-training, and then a specific shaping to the final product. Finally, transformer is the type of machine learning system. GPT 3.5 was current as of December 2022. GPT 4.0 was released in March 2023, and likely new versions will be arriving. Progress, or change, in the research area of LLM chatbots is extremely rapid. Anything written here right now will be out of date in days or weeks. Please be aware of that. We know what LLMs are, how they are produced, and how they work, to a degree. That can be described. There is another caution besides the changing landscape. The large language models are so complex that there is no real description, explanation, or analysis of the details of their internal workings. Likely this will not change anytime soon. ChatGPT, using GPT 3.5, can write high school to college level essays to about an A standard. The written English is definitely of a standard, and usually the factual content, if that is required or appropriate, is also of a quality. This means that it can write essays for students, articles for journalists, and sometimes, or almost, write research papers for researchers. Tell jokes, write poetry, and produce cooking recipes. Write or correct computer programs. This also is carried out to a high standard. This makes it a valuable programming or debugging tool. OpenAI and GitHub had earlier developed Copilot, which is a programmer's assistant, GitHub 2022. Copilot's abilities seem to be built into ChatGPT. As part of chatting, ChatGPT can answer follow-up questions, admit its mistakes, challenge incorrect premises, and reject inappropriate requests, OpenAI 2022a. It does have some weaknesses, which we will look at further in the next chapter. But briefly, it is not good on basic mathematics and arithmetic. Its knowledge is not current. Its training data is from pre-2020. This means that it has no knowledge, for example, of recent politics or sporting events. Sometimes it can go completely wrong. For example, some users have reported of occasions when ChatGPT has referred to books that do not exist. The weaknesses that it has have been fully acknowledged by OpenAI, and many of them will be addressed in short order. Nevertheless, just what it can do is astonishing. It can produce, or generate, grammatical correct and sophisticated English that in most cases could not be distinguished from that written by an educated native speaker. It also has, or appears to have, extensive factual knowledge. There is an example above, section 2.4 on the Turing test. There are a plethora of examples of ChatGPT output available online. There were 1 million registered users within a couple of days of its research release on November 30, 2022, and almost all of those published their experiences on social media, discussion sites like Reddit, or in online journals or newspapers. This research release does not reveal everything about its capabilities. For example, it seems to have a problem with truth. It writes plausible English, but seems to do that without knowing whether what it is saying is true or has evidence in its favor. Contrast this with the Google search engine. If you asked that about the Turing test, it would return a ranked list of links. ChatGPT seems much better here, just from a user interface point of view. But if you wanted to reassure yourself, when using Google search, you could follow some or all of the links and get a sense of the foundations or grounding of what the contents of the links were asserting. With ChatGPT, truth, fiction, and well-formed writing seem all to run into one. On tricky topics, or more complicated concepts, ChatGPT sometimes gave highly plausible answers that are flat-out wrong, something its creators warn about in their disclaimers. It may be, so to speak, that ChatGPT knows why it says what it does, but we are not fully aware of that at this point. It has been said fiction is what ChatGPT is really good at. 2.8 Task-oriented. Most task-oriented dialogue agents, including Siri, Cortana, Alexa, and OK Google, use Genial Understander System, GUS, architecture, Bobrow et al. 1977, Daniel Jurafsky and Martin 2021.
GUS, Genial Understander System, is intended to engage a sympathetic and highly cooperative human in an English dialogue, directed towards a specific goal within a very restricted domain of discourse. There is good reason for restricting the domain of discourse for a computer system which is to engage in an English dialogue. Specializing the subject matter that the system can talk about permits it to achieve some measure of realism without encompassing all the possibilities of human knowledge or of the English language. It also provides the user with specific motivation for participating in the conversation, thus narrowing the range of expectations that GUS must have about the user's purposes. A system restricted in this way will be more able to guide the conversation within the boundaries of its competence. Bobrow et al. 1977.
This GUS architecture is not itself a ML architecture, rather it is an older AI frame and slot design. The implementations do use natural language, English, say, and so the modern dialogue agents will use recent NLP machine-learned techniques. A frame is a mini-world, or situation, or ontology, that captures everything that either is known or needs to be known about a certain setup. For example, consider an online takeout system for a restaurant. There will need to be a menu, with appetizers, entrees, desserts, etc., a recipient's name, address, payment details, and so forth. These constitute the frame, or perhaps even several frames, and the frame has slots, one for the appetizers, one for the credit card number. The slots will have types. For example, the purchaser's name is a string, e.g. John Smith, and the credit card number is a number, e.g. 1234-5678-9100-1234. What GUS will aim to do is to be genial while filling all the requisite slots with values of the required type. In principle, it really is not a lot more difficult than form filling. After all, you can order takeout from a form on a web page. Adding a voice interface makes the process harder. Different computer programmers may well organize the algorithms for a GUS architecture in different ways. We can sketch here the general approach of the 1977 original. The program will try to retain the dialogue initiative as much as possible. There will be an agenda loop of events or tasks to be done. This pattern is standard event loop, or real-time, processing. The program will keep going around the loop until it meets an exit condition. Tasks can be added to, or removed from, the agenda. Tasks can be suspended, to be revisited later. There will be an overall frame with slots, and possible many subsidiary frames with their slots. The event loop of tasks will aim to fill all the slots that need filling. Some slots may be able to be left open in certain circumstances. Many of the slots will have their own subprograms, which will be invoked when the slot is filled. For example, two slots might need the same value, e.g. a departure city in a reservation system. Then each of these slots might have small program to put a value for the departure city into the other slot, if required, when its own value is filled. Verbal or textual input will be able to be taken at any time and added to the processing loop. Output, i.e. responses, will be given at the program's direction. The actual processing of the dialogue will be where the real difficulties lie. There will be morphological processing, to pick up the words, syntactical processing, to pick up the sentences, and a good amount more to make sense of the vagaries of dialogue and to fit the results into the overall state of the system. Also, the filling of the slots will itself often require interfacing with one or more databases, for example, to look up the departure times of the trains or airplanes.
Chapter 3. Language Models. 3.1 Introduction.
Many of the modern AI systems have their origins with language models. These typically use text as input and produce text as output. Language models have a huge advantage when considered as an ML research challenge. They can be trained on unlabeled text, and there is plenty of that, for example, the Internet. Elsewhere, any ML program, trained by supervised learning, will need a quantity of high-quality labeled data, and that is hard to come by. But most language models will be able to be trained by self-supervision using digitized text. Emily Bender and her co-authors explain language models as:
The term language model, LM, refers to systems which are trained on string prediction tasks, that is, predicting the likelihood of a token, character, word or string, given either its preceding context or, in bidirectional and masked LMs, its surrounding context. Such systems are unsupervised and when deployed, take a text as input, commonly outputting scores or string predictions. Bender et al. 2021.
What does this mean? Some background theory will be useful here.
3.2 Markov Chains.
Alexander Pushkin, the eminent Russian poet, playwright, and novelist, writes,
My uncle's goodness is extreme, if seriously he hath disease, he hath acquired the world's esteem and nothing more important sees, a paragon of virtue he. But what a nuisance it will be, chained to his bedside night and day without a chance to slip away. Ye need dissimulation base a dying man with art to soothe, beneath his head the pillow smooth, and physic bring with mournful face, to sigh and meditate alone, when will the devil take his own? Pushkin 1881.
This is from an English translation of Eugene Onegin, a romance of Russian life in verse written in Russian. There is an interesting tidbit of information associated with this. Until about 1900, probabilistic analyses of common sequences of apparently random events assumed that the individual events were independent one from another. So, as examples, that the second and subsequent throws of a single gambling die are not influenced in any way by the earlier throws, and that the outcome of a spin of a roulette wheel does not depend on the spin, or spins, that went before. The Russian mathematician Andrei Andreevich Markov questioned whether this independence assumption held of all sequences, especially in fields outside of gambling. He conjectured that it did not and produced a suitable mathematical theory to cover the case. The basic theory is relatively easy to understand. Almost everybody is familiar with the centuries-old board game Snakes and Ladders. In this, there is a board with 101 numbered squares on it, and players advance from the start, i.e. 0, to 100 by repeatedly throwing dice and using the numbers they obtain. The first player to 100 wins. On the board there are some snakes and some ladders. These connect pairs of numbers, usually separated by 5 to 20 intervening numbers. The heads of the individual snakes are higher of a higher number than the tails. If a player lands on the head of a snake, they have to go backwards to the tails, losing some of their advance. If a player lands on the base of a ladder, they advance to the top of that ladder. Consider just one player and one die, and assume the player throws a 5. This may advance the player 5 spaces, but it also may send the player back some spaces, or it may send the player forward more spaces than 5. What happens depends in part on what square the player is on. Throwing a 5 when on square 15 might produce an entirely different result, in terms of going forward or backward, than throwing a 5 when on square 32. The square that the player is on is the state. The throw of the single die will produce one of 6 numbers. This will move the player to one of 6 other states. The values of the throws, in this case, are equally probable, and so there are 6 equally probable non-zero transition probabilities from the current state to the next state. What happens with the throw depends only on the current state and the value of the throw. It does not depend on the state before the current state, or any before that, i.e. on the history of the individual game. For example, if a player is on square 27, state 27, that is all that matters. It does not matter how the player got to 27. Snakes and ladders play is an example of a Markov chain. Conceptually, there is usually time, or a time step, or time beats, involved in producing the sequence of states in a Markov chain. If we wanted to build that into the example, we could just require that the player throws the die every 30 seconds. There are a few other details that can be added to the snakes and ladders example to make it closer to Markov chain theory. There is usually a start state, or a probability among the states for one being the start state. So, the 0 square would have a probability of 1 of being the start state, and the other states 1 to 100 probability 0. Similarly, there might be a terminal state. If so, there would be no transition probabilities for a move out of the 100 square. Also, it is not possible to rest on the foot of a ladder or the head of a snake, because the player would be required to move on elsewhere. This could be represented either by having no transition probabilities that end with the foot of a ladder, or the head of a snake, and including the jumps in with the dice values, or just by omitting those states altogether. Summing up Markov chains, there is a sequence of events, states, transition probabilities, and the dependence on the state is just with the current state. This gave him a value for the overall probability of a particular character being a consonant or being a vowel. He then looked at pairs of consecutive characters and what the probabilities were for the second character being a consonant or a vowel if the first character was a vowel or a consonant. These are transition probabilities from vowels to consonants and consonants to vowels. What he found was that vowels were more likely to be followed by consonants, and consonants by vowels, that the transition probabilities were different to the overall probabilities. What this meant was that if the text was thought of as a sequence or stream of letters, the appearance of one letter after another was not an independent event, being governed by only the overall probabilities of the letters. Rather, it was a dependent event having a dependence on the current letter or state. From here, there is the theory and mathematics of Markov chains. Markov chains are everywhere. They are in text. Not just with consonants and vowels, but also with letter sequences like you following Q, and word sequences like the word he being followed by a verb phrase. They are in spoken text, or speech, with sequences of phonemes, certain sounds follow others. They are in the weather, rainy days tend to follow other rainy days. Many games, the sequences of their moves can be analyzed by Markov chains, e.g. chess. The stock market can be seen as a Markov chain. Bull markets tend to be followed by bull markets, and bear markets followed by bear markets. There are many Markov chains in biology, for example with DNA sequences. More zero or less any values or measurements that change over time, such as prices in a stock market, speeds of motor cars, etc., can be modeled by Markov chains. There is a paper 5 Greatest Applications of Markov Chains, von Hilgers and Langeville 2006. It is recommended. 3.3 Hidden Markov Models. Hidden Markov models, HMMs, are extremely common in the ML analysis of sequential data that has a dependence on time. Typically, a model will be able to explain a sequence and predict or generate new sequences. The techniques are most at home with natural language processing, NLP, and with handwriting recognition, speech recognition, and biological informatics. With an HMM, there are two collections of probabilities. In the background, there is a probabilistic Markov chain or process as explained above. But some, or all, of the states of this Markov process are hidden and unseeable directly by observers. However, the hidden states emit observations which can be seen or observed. These emissions of observations are themselves governed by probabilities relating them to the hidden states. An example might help with understanding the setup. Suppose we are interested in the sequences of year-on-year climate values in New Zealand from 1,000 years ago. We may be very interested in this because the climate affects the environment, its flora and fauna, and their history and development. Suppose the years can be just hot or cold, and which they are for a particular year depends solely on whether the predecessor year is hot or is cold. Suppose also that the probabilities of a hot year being followed by another hot year and a cold year being followed by a cold year are all known from modern values, which are assumed to be unchanged from those of 1,000 years ago. These ancient weather sequences are Markov processes, and their states are hidden and not directly observable. However, the weather affects tree ring growth, and we have modern probabilities relating that growth to the weather, which, again, are assumed to be unchanged from 1,000 years ago. More than a few New Zealand kauri trees live longer than 1,000 years. So, the kauri rings can serve as modern emitted observations on the hidden Markov process of ancient weather sequences in New Zealand, stamped 2017, Rabina 1989. We will not address the mathematics in detail here. But what the mathematics can do is estimate the probabilities for a hidden sequence, give the observable sequence, and the other relevant probabilities too, estimate the probabilities for an observable sequence, given the hidden sequence, and the other relevant probabilities. 3. Given an observable sequence, the number of hidden model states and different types of observations, can use successive approximation on the parameters to produce values which give the greatest probability of yielding the provided sequence. The successive approximation uses what is known as gradient descent. See the excellent videos from Josh Starmer or Grant Sanderson for explanations of gradient descent, Starmer and StatQuest 2019, Sanderson and 3 Blue 1 Brown 2017b. Gradient descent is a standard ML technique. As mentioned, natural language processing often uses HMMs. Mark Stamp, in his Stamp 2017, gives a simple example of language analysis, which is more or less the inverse of Markov's Eugene Onegin case. Say you gave Marvin the Martian, an alien, a corpus of 1,000,000 words of actual English text and invited him/them to investigate sets of individual characters under the assumption that there was a HMM with two hidden states that was producing the observed English. The result of Marvin's research would be that there were two relevant sets of letters, and they would be the vowels and the consonants. Initially, Marvin knows nothing about English, yet Marvin can learn structural and statistical properties using an HMM. Marvin and Markov, in the Onegin example, are looking at individual characters or letters. But what is much more useful and widespread in the general NLP case is analyzing entire words, or parts of words, and, for example, tagging them with their parts of speech, POS. In this, HMMs are often used to identify nouns, verbs, adjectives, determiners, etc. Parts of speech point to the function of the words in the sentences, i.e., they hint at role or meaning. 3.4 Shannon's Guessing Game. 3.4.1 Introduction. An interesting precursor of modern NLP research is the 1940s work of Claude Shannon on signal information, C. E. Shannon, 1948. Shannon provided an extensive analysis of the natural language English, and it is worthwhile to follow and develop his reasoning. He was trying to calculate how much entropy, signal information, there was in passages of English. What entropy and signal information are need not concern us. The approach here was to use successive approximation by models. Shannon's zero-order model assumed that the alphabetic letters or characters had an equal probability of occurring in English text. But in real English, assuming here that the speaker or writer is not idiosyncratic, the occurrence of letters is not equiprobable. E, for example, has a probability of 0.13 of occurring and W a probability of 0.02. If the differing probabilities for all the letters are taken into account, that produces what is known as the first-order model. There are also conditional, or transition, probabilities relating letters and letter sequences in English. Q, for example, is almost invariably followed by U. This model is now using a Markov process for analysis. Two-letter sequences, giving the second-order model, can be considered, or three-letter sequences, and so on. A similar approach can be adopted to predicting a missing word or the next word, using whole words as the alphabet and not just single letters. Filling in the blanks in some text is known as a closed task. These will be explained in more detail shortly. The assumption of non-idiosyncrasy of the source English text is entirely in order. John Pierce tells us of E.V. Wright, who published the 267-page novel Gatsby, in which there are no E's, Pierce 1980, page 48. There is an important point to be made here. When there is focus on the probabilities of occurrences of letters in text, say E's, there is a need to address context. Such probabilities may well have different values depending on, for example, whether the text is Gatsby, the Sunday Times, or every piece of English on the Internet. Care is also needed here with the relation between the training data and the intended real-use data, the test data, for ML language probabilities. You would not want to use Gatsby as the sole training data for all of written English. Shannon conducted extensive experiments on English. One technique he used was to give test subjects many letters of a sequence of English, usually up to about 50 letters, and then ask them to guess the next unknown letter, a closed task. He found that the subjects were able to guess correctly about half the time or more. You can try Shannon's experiment or game. Pick roughly the middle letter of any line in this book, count forward 50 letters, keeping the 51st letter covered before making your guess, and see how uncertain you are about the value of the 51st letter. The results show that English is massively redundant. This redundancy has its advantages. Natural languages are highly noise-tolerant. Often many letters in a message can go missing or be mistranscribed, and yet still the receiver will be able to reconstruct the original. And also, yet again, as Shannon pointed out, without redundancy, crossword puzzles would be impossible. English is usually taken to be an ergodic source. Roughly, that means that one reasonable passage is a good representative of the whole, as far as all the probabilities are concerned. However, so-called large language models and foundation models would typically use vast amounts of text as input data. See, for example, Common Crawl 2022. There is a good reason for that. As we will see, these models are trying to do more than evaluate probabilities. They are, for example, also trying to acquire knowledge, such as the fact that George Orwell is the author of the book 1984. 3.4.2 Shannon's approximations as Markov processes. To explain the GPT large language models, there is a passage in the Shannon paper which is pure gold. To give a visual idea of how this series of processes approaches the language, typical sequences in the approximations to English have been constructed and are given below. In all cases, we have assumed a 27-symbol alphabet, the 26 letters, and a space. 1. Zero-order approximation, symbols independent and equiprobable. Xfammelrixkirchfuge ZLPWCFWKCYJ Jeefsgid Pamp Zasisibzol HJQD. 2. First-order approximation, symbols independent but with frequencies of English text. OCROHLIRGWR Nilwis EULL Nasibia THEEI Alhenpa Oupva Na BRL. 3. Second-order approximation, diagram structure as in English. On IE Antsutnis RT Inktor STBS Demi Achen D Ilonasiv 2 Ku at Tizenair FUSO Tizen Anditope Cis Tisby. 4. Third-order approximation, trigram structure as in English. In Noist Lat way Kratikt Frauer Burrs Grosset Pondenome of Demons Tours of the Reptigen is Rego Actiona of CRE. 5. First-order word approximation. Rather than continue with tetragram, n-gram structure, it is easier and better to jump at this point to word units. Here words are chosen independently but with their appropriate frequencies. Representing and speedily is in good apt or come can different natural here he the a in came the two of to expert gray come to furnishes the line message had be these. 6. Second-order word approximation. The word transition probabilities are correct, but no further structure is included. The head end and frontal attack on an English writer that the character of this point is therefore another method for the letters that the time of whoever told the problem for an unexpected. The resemblance to ordinary English text increases quite noticeably at each of the above steps. Note that these samples have reasonably good structure out to about twice the range that is taken into account in their construction. Thus in 3, the statistical process ensures reasonable text for two-letter sequences, but four-letter sequences from the sample can usually be fitted into good sentences. In 6, sequences of 4 or more words can easily be placed in sentences without unusual or strained constructions. C. E. Shannon 1948, 7. Shannon starts here with equiprobable letters, the zero-order approximation, then moves to allow the letters to have the probabilities that they do in real English. Then, with the second-order approximation, he allows the letters to have transition probabilities dependent on the single preceding letter only. So, if the preceding letter were Q, for example, the probability of the next letter being Z would be 0, the probability of it being U would be high, the probability of the next letter being a blank space would have some positive value, and so on. At this point, what is going on is a Markov process. Shannon tells us this: stochastic processes of the type described above are known mathematically as discrete Markov processes and have been extensively studied in the literature. C. E. Shannon 1948, 8. The preceding letter in the second-order approximation is a state or context, and the relevant probability depends on that state. The third-order approximation uses transition probabilities, but this time extends the state or context to the two preceding letters. At this point, Shannon switches to using entire words, not individual letters, and that is not of further interest to us here. A point to note is that 1948, Shannon would have had no way of calculating transition probabilities using 3, 4, 5, and so on preceding letters. Basically, you need computers and digitized text to do that. Had he been able to do so, no doubt he would have explored much larger contexts. 3.4.3 Training a Shannon Markov Model to produce a baby GPT. Nowadays, we can train a Shannon Markov model to evaluate the transition probabilities for itself, using self-supervised learning. The result is what is in effect a GPT, a generative pre-trained transformer. Andrei Karpathy suggested the following as an example: Karpathy 2023a. There are some serious simplifications in this. The alphabet consists of two tokens, A, B. The context, or prompt, is the three preceding letters. So, there are 8 states, namely AAA, AAB, ABA, ABB, etc. There will be 16 transition probabilities from the contexts to the next token. These probabilities need to be determined from the training data by training. We can note, though, each context can produce either A or B, and if the probability for one of those is X, the probability for the other is 1X. So, there are 8 values to be pinned down. The training data, the training text, is the sequence of 15 tokens. What our ML system is going to do is to produce a next token as an output, then do that again and again to give 15 tokens. It needs a 3-token context to start with. So, we will give it 3 as its initialization or prompt. Then let it run to produce the next 12 tokens. Just to explain further. The first prompt will produce an output token, say B. Then, the new token gets included in the next prompt and first token in the earlier prompt gets dropped out of the prompt, and A, say, is generated. So there is a continuous adding and dropping and sliding forward. The ML system sees only 3 symbols at a time, the ones shown in green, but those 3 symbols change through time. Suppose, for the first training round, it completes its generation and produces. This output will be compared with the training data. There will be a scoring system that evaluates it. Then the machine learning model will revise its internal weights, i.e. parameters. It will improve itself. And there will be a second training round, and a third, and the process will be repeated over and over. Karpathy has provided sample software to do this, and typically there might be 50 rounds of training. In his publication, the training determined the transition probabilities to be AAA-A with probability 0.45. To take 2 examples from this, the context AAA appears 6 times, and asterisk picks them. 3 of these are followed by A, and 3 followed by B. So, roughly speaking, we might expect that both would have a probability of near 0.5. In fact, the published training run gave 0.45 for one and 0.55 for the other. For the second example, the context ABA appears twice, identified by an exclamation mark, and each time it is followed by an A. So, ABA-A should be 1.0 and ABA-B should be 0.0. The published training run gave 0.78 and 0.22. There were only 50 rounds of training. If more rounds were used, the values would sharpen to the correct values. Notice that some of the possible contexts do not appear in the training data. For example, BBB does not. So, what should happen with a BBB context is an open question. It is not determined by the training data. It is at this point that what is called inductive bias enters. The system needs to make a reasonable guess, and with the Karpathy sample implementation it goes with 0.5 chance of getting an A, and 0.5 of getting AB, for all contexts it cannot determine from the data. At this point, we have a baby GPT. It is a Shannon/Markov model with a context of 3 preceding tokens. It can generate output. Here's one example that it produced. To compare the baby with a GPT like GPT-3. Our alphabet has 2 tokens. A full-blown GPT would likely use words and not individual letters in its alphabet, and it might have an alphabet of 50,000 different tokens, words. Our context is a context of the 3 previous tokens. A full-blown GPT might use a context window that can see the 30,000 previous tokens. As of May 2023, Anthropic's Claude model has a context window of 100,000 tokens, which is about 70,000 words. Its tokens are larger than single characters, but smaller than entire words. Our training text is 15 tokens long. GPT-4's training text is more or less the entire internet. We can train in milliseconds. GPT-4 takes months on parallel supercomputers. The baby was trained on 50 rounds, epochs, of training. OpenAI has not disclosed how many epochs of training it used. We asked GPT-4 this question, but it will have been in thousands.
3.5 Taylor's closed procedure.
In 1953, Wilson L. Taylor published the paper Closed Procedure, a new tool for measuring readability, W. L. Taylor in 1953. Basically, closed procedures amount to taking some text and deleting parts of it, then inviting the human subjects, or software, to fill in the blanks to recreate the original text. Taylor writes,
Given chickens cackle and quack, almost anyone can instantly supply ducks. Note that the sentence pattern is a complex one made up of many subpatterns. One must know not only the meanings, i.e., patterns of symbol-meaning relationships, and forms, patterns of letters, of all the 5 words, but also the meanings of given combinations of them, plus the fact that the sentence structure seems to demand a term parallel to cackle but associated with ducks instead of chickens. In other words, one must guess what the mutilated sentence means as a whole, then complete its pattern to fit that whole meaning. W. L. Taylor, 1953.
As the title of his paper indicates, Taylor's original idea was to use closed procedures as one tool to assess the reading skills of subjects. But subsequently their use has expanded far beyond this. Closed tasks, or closed procedures, are reasonably demanding, and they are a popular research technique for modern natural language processing, NLP. Nowadays, it is a common practice for researchers to write, mask, to show where the blanks are. So, Taylor's illustrative sentence would be written given chickens cackle and mask, quack, almost anyone can instantly supply ducks.
3.6 Nano GPT and an illustration of training.
Andrei Karpathy has provided for us Nano GPT, Karpathy, 2022-2023. This is some software you can run at home. Do try it. It is the simplest, fastest repository for training/fine-tuning medium-sized GPTs. It can reproduce GPT-2, Karpathy, 2022-2023. NanoGPT is a language model, and it can be used to illustrate training. Adish Bhatia has done exactly that in the implementation he calls Baby GPT, Bhatia 2023. One of the examples that Bhatia provides concerns Jane Austen. To paraphrase Bhatia, Baby GPT is provided with the 800,000 words of Jane Austen's work and also a prompt. You must decide for yourself, said Elizabeth. We assume here that this prompt is not among the actual work of Austen, otherwise that would ruin the training, inviting what is called overfitting. Here this means that it has been told an answer in its training. And what Baby GPT has to do, its task, is to produce the next 70 or so words written in the style of Jane Austen. The process will be for it to output about 700 characters, one at a time. It will produce one character. Then, having done that, produce the second character, and so on, until it reaches about 700 characters. A blank space is a character, as are punctuation marks and uppercase characters. Thus, some character sequences will have the appearance of sequences of words, or even of phrases and sentences. There will be a scoring system that evaluates the mistakes. Learning will be used to change the parameters of baby GPT. Then this will be done again and again, forming round after round. In the first round it produced "You must decide for yourself," said Elizabeth. GRTHBE 22, I10 and ZOJ1A2 UTWMOZVSA.F0JC1HPNDRSR6 to 8J7DCV/HWRWFYYGRX8 ILC. WAE, LTZ F8 and or 6D KDD 77WQY4 NTV, N, and more. Here, it is producing characters randomly, of equal probability. This is Shannon's zero-order model. Were this first round to be run again, with the parameters reset to their original values, the output would likely be different. A character set, with special characters in it, might have a repertoire of 256 different characters. So, the probability for any particular character appearing in any particular position is 1/256. Getting the same output sequence twice is very unlikely. After 250 rounds of training, it produced "You must decide for yourself," said Elizabeth Gra Busratind the Utharth Esatachanders Indi Shadito the Se Orer Othino A the Thetlf W Wada Sire, and more. This is now similar to Shannon's first-order model. It has figured out that not all letters are equiprobable, for example, that special characters do not occur very often and that E's occur relatively frequently. After 30,000 rounds it produced "You must decide for yourself," said Elizabeth rather repeatedly. "That is very agreeable displeasure. They will ever be a lively young woman as it will be more disagreeable. My dear Fanny," and more. Now there are words, sentences, some grammar, and a character stream approximating English. This training was carried out on a laptop computer in an hour. Some of the large language models, which we'll get to shortly, might use what effectively is a supercomputer for months for their training. Also, they may use a two-stage training. There might be a pre-training, which would be a self-learning training similar to the above. This then might be followed by reinforcement learning, where there is a panel of about 40 human judges giving feedback and a scoring as to the quality of the output. 3.7 Embeddings.
In machine learning, an embedding is a way of representing data as points in n-dimensional space so that similar data points cluster together. Markowitz 2022.
A point in an n-dimensional space can be thought of as a list, or vector, of numbers. As examples, a point in a two-dimensional space might be 2, 3. A point in a three-dimensional space might be 1, 29, 2. A point in a seven-dimensional space might be 29.1-7, 2.9, 13, 21.6-37.23, 9. You get the idea. Then a measure can be put on these lists that will show whether two or more lists are similar. If they are, this means, or might mean, that the underlying data, the relevant underlying data points, are similar. Embeddings are important.
Embeddings power 1. Recommendation systems, i.e. Netflix style. If you like these movies you'll like this one too. 2. All kinds of search. A. Text search, like Google search. B. Image search, like Google reverse image search. 3. Chatbots and question answering systems. 4. Data preprocessing, preparing data to be fed into a machine learning model. 5. One-shot/zero-shot learning, i.e. machine learning models that learn from almost no training data. 6. Fraud detection/outlier detection. 7. Typo detection and all manners of fuzzy matching. 8. Detecting when ML models go stale, drift. 9. So much more. Markowitz 2022.
We will get to most of these applications later. 3.8 Word embeddings and Word2Vec. Word embeddings are a common and useful tool or technique to process words prior to their being used in ML models. Often the embeddings can capture useful deep syntactic and semantic information. The DL models themselves use numbers internally for their arithmetic and mathematics. This gives the preliminary task of converting words to numbers for use in the models. This coding could be done trivially by using the number 1 for the first word, 2 for the second word, and so on. But notice this. Say word number 3 was toy and word number 47 was toys. Those two words are similar to each, one is the plural form of the other. But information of that similarity is lost in the coding. The numbers 3 and 47 are not similar, nor do they give any hint of similarity between the words that they are coding. Tomas Michalov and fellow authors, following earlier work, proposed and developed the technique of using vectors, lists of numbers, to code the words. Michalov, Chen, et al. 2013, Michalov, Sutskever, et al. 2013, Michalov, Yi, and Zweig 2013, Collier 2016, Alamar 2019. The idea here is that in a large corpus of text the word toys, for example, appears in various contexts, that is, surrounded by other words e.g. children, Christmas, and so forth, and it tends not to appear in other contexts, e.g. surrounded by words about the fourth quarter of the Super Bowl, then some aspects of these appearance contexts can be placed into the vector that is to represent toys. Similarly for the word toy and its contexts. The overlap of the contexts gives information about the words. This type of coding, exemplified in the software word 2vec, can capture similarities and also some real information. It can open the way to answering questions like Paris is to France as mask is to England. The famous example that word 2vec is known for is king, man plus woman equals queen. We are using a rough representation here of vectors and vector arithmetic. But what word 2vec is telling us is, if you take the concept of king, take the man out of it, add a woman to it, you get the concept of queen. Word 2vec has reached this conclusion merely by being trained on a large corpus of text. Word 2vec is not the only way of producing word embeddings, nor is it the best for all circumstances. But, the point is, the use of intelligent word embeddings on a large corpus of text can provide to ML/NLP programs input that has some syntactic and semantic information built in. 3.9 Adding knowledge to language models. In the case of natural languages, language models, in their original and simpler forms, had to manage words, parts of speech, grammar, and so forth. They did not address knowledge or truth or meaning or reference. So, for example, if such a model produced, for some purpose, some entirely correct syntactical and grammatical output such as the Mississippi is the longest river in the world and it is 30 miles long, that would be perfectly good, and the fact that what is being asserted is mistaken is beside the point. This has consequences for the training data. The data needs to be good sample English, say, with all its varying genres, styles, and diversity. But it does not need to be vast and encyclopedic in its content. It does not need, for example, to contain simple, if obscure, everyday facts like the name of the secretary of the Teamsters Local Union LU number 2. For those with an inquiring mind, that name is Aaron Foley. But we have already seen value in many settings to add knowledge to ML systems. For example, a reservation chatbot, a task-oriented dialogue agent, linked to a database, can book airline flights and be absolutely correct on the schedules and prices, etc. It does not take a huge stretch of the imagination to realize that many published texts contain knowledge. For example, a favorite children's book, Bertha Morris Parker's The Golden Book of Facts and Figures. A treasury of information on hundreds of subjects with more than 500 pictures in color does, so do many encyclopedias, and, indeed, Wikipedia. Most of our knowledge is in books and libraries. Presumably a language model could be configured to take on closed challenges like the mask, river is the longest river in the world, and answer it with Amazon. Actually, many ML question answering systems can do exactly this. Further, Fabio Petroni and his fellow authors inform us that larger language models are developing this ability, Petroni et al. 2019. There is an interesting and important point here. Historically, the way that ML systems would interact and interface with knowledge in text is by producing or extracting from the text a database and then addressing queries to that database. But this is not easy to do, for a variety of reasons. Databases, with their tables of rows and columns, need design. They need ontologies. Different databases may well have different ontologies and be information silos unable to share their knowledge one with another. Also, the training of database extractors would likely need to be supervised training, i.e. training that used labeled data, and once labeled data is required, a project becomes much more challenging. Then the questions to a database have a structured semi-formal logical structure, and these might not sit easily with users' expectations. But research now seems to indicate that making the language models larger and training them, unsupervised or self-supervised, on more expansive corpuses of text, gives those models question answering and knowledge manipulation abilities that are superior to the earlier database extraction techniques, Lewis, Denoyer, and Riedel 2019. Of course, research can be revised by further research, and promising research can fade to nothing. But right now, 2023, it looks as though making the language models larger and trained more extensively will yield gold. 3.10 Instruct GPT and the insights it provides. As of January 2023, language models, and ML in general, have been well and truly being brought to the world by ChatGPT and similar astonishing ML programs, OpenAI 2022a. ChatGPT was created by OpenAI, with $1 billion or more funding from Microsoft, and more funding from others, OpenAI 2022c. Google and Facebook, and maybe other commercial companies or institutions, have similar programs, e.g. Bard and Llama. OpenAI have not to date published information on how ChatGPT works, and they may not do so in detail. They are a for-profit commercial company. However, they have said that it works the same way as Instruct GPT, which is one of their earlier programs, and they have published a thorough research paper on Instruct GPT, Ouyang et al. 2022. We should look at Instruct GPT. Long Ouyang and his fellow authors provide the following abstract to their paper: making language models bigger does not inherently make them better at following a user's intent. For example, large language models can generate outputs that are untruthful, toxic, or simply not helpful to the user. In other words, these models are not aligned with their users. In this paper, we show an avenue for aligning language models with user intent on a wide range of tasks by fine-tuning with human feedback. Starting with a set of labeler-written prompts and prompts submitted through the OpenAI API, we collect a dataset of labeler demonstrations of the desired model behavior, which we use to fine-tune GPT-3 using supervised learning. We then collect a dataset of rankings of model outputs, which we use to further fine-tune this supervised model using reinforcement learning from human feedback. We call the resulting models Instruct GPT. In human evaluations on our prompt distribution, outputs from the 1.3b parameter Instruct GPT model are preferred to outputs from the 175b GPT-3, despite having 100x fewer parameters. Moreover, Instruct GPT models show improvements in truthfulness and reductions in toxic output generation while having minimal performance regressions on public NLP datasets. Even though Instruct GPT still makes simple mistakes, our results show that fine-tuning with human feedback is a promising direction for aligning language models with human intent. The idea of alignment needs explaining. This really is the notion of the ML system being able to do what it is supposed to. It should align with the user's and designer's intent and desired behavior. In the case of the language models discussed to date, desirable models going forward should be able to produce text, which is appropriately true, helpful, and not offensive. It looked as though plain Markov-Shannon closed-style next token predictors could not and would not be able to do this in its entirety. However, larger language models, trained by self-supervision, and perhaps with word embeddings, etc., seem to be progress along the way. Ouyang et al. Used the following diagram to explain their training technique. F2. The path the Ouyang et al. Follow is first to involve the user by inviting textual prompts from the users. These prompts, in 10 categories, might be asking questions, inviting explanations, giving examples of the task, and so forth. This gave the researchers a database of prompts. Human labelers, assisting the researchers, also wrote some prompts. Then about 10,000 samples were taken from the prompts and desired answers written to them by human labelers. Answers were also obtained from pre-trained, but not fully trained, baseline versions of InstructGPT and GPT-3. Then different answers to the same prompts were ranked by humans, the labelers, as to better answers and not so good answers. This allows the incipient InstructGPT system to develop a reward model. A reward model, or schema, or system is a requirement of reinforcement learning C Section 2.8. At this point, the system is able to rank responses, although, on its own, the ability to rank does not guarantee the generation of good responses, just as a chess-playing AI system may recognize good board positions without being able to produce them. Finally, InstructGPT is encouraged to improve itself by reinforcement learning. Roughly, it generates responses, sees how good or bad they are, and modifies itself in the light of what it is seeing. Running reinforcement learning at large scale typically was hard to do, maybe even approaching being impossible at a practical level. But the OpenAI researchers developed new techniques that overcame those difficulties. There is an important issue at the core of this. The reward model relies on human judgment as to what is good and bad. The labelers, around 40 of them, produce the judgments. There are quality assurance techniques from research methods that use human judges, such as checking for intersubjective reliability and other desirable properties. These techniques provide guardrails. Ouyang et al. In their paper are conscientious and thorough. There are no shortcomings, or apparent shortcomings, whatsoever. Nevertheless, with assessment by a group of people, there is always the possibility that different groups with a different composition, would judge differently. We have only to think of juries in courts of law. Both the prosecution and the defense focus on obtaining the composition of the jury that suits their purposes. They would not do this if composition of juries did not matter. With ML systems, there is often a concern with bias and diversity, and so there should be. With large language models in the style of InstructGPT and ChatGPT, there is the huge corpus of text that they are trained on, and there are the human judgments that provide input to the reward model. The latter needs attention.